For our linear algebra project, we got cryptography. Cryptography is a way to encode messages in a way that rearranges the letters so that it's unreadable to a person that does not have the key. Our method of cryptography decided to be the Hill cipher. The Hill cipher focuses mainly on using linear algebra aspects such as matrix arithmetic and modular arithmetic. For our example today, we're going to be using a 2x2 matrix in order to encode and decode our messages. So to start, the first step is you have to write out your alphabetical zero-based indexing. This means that each letter starting from A all the way to Z must be paired with a number starting from 0 to 25. So A goes to 0, B goes to 1, C goes to 2, all the way down until Y is at 24 and Z goes to 25. Our next step is to pick a keyword. For our particular example, our keyword is going to be pi. If your keyword's length is less than the total number of elements in the matrix that you will be using, you are going to have to add on extra letters, starting with A, then B, then C, and so on and so forth. If your keyword is longer than the total number of elements in the matrix you're using, then you will have to cut off that keyword to fit into your matrix. Step 3 is to put our keyword into your n by n matrix, but for our example, it will be 2x2. So since our keyword is only 2 letters instead of 4, we have to add a few letters. So our key matrix will end up looking like this: P, I, A, and B. Next, step 4 is to translate the letters of our translation matrix into numbers. Using our alphabetical zero-based indexing, we can denote that 15 goes to P, 8 goes to I, 0 to A, and 1 to B. Step 5 is to choose a plain text or message that has had nothing done to it that you would like to send and encrypt that. So for our example, our plain text will be math. Step 6 is to translate that text into a series of n by 1 column vectors. For our example, since our encryption matrix is a 2x2, our column vectors must be 2 by 1, because later they will be multiplied together. So since our plain text is math, our column vectors look like MA and TH. Step 7 is to translate these column vectors into numbers. We know using our alphabetical zero-based indexing that 12 goes to M, 0 to A, and then 19 to T, and 7 to H. Step 8 is to multiply the keyword matrix by each column vector. So the keyword matrix that we found earlier, 15, 8, 0, 1, is multiplied by 12, 0, resulting in 180, 0. Then again, 15, 8, 0, 1 multiplied by 19, 7 results in 341, 7. Step 9 is to take the resulting column vectors mod 26. Mod 26 allows us to make sure that every number in our column vector is within the range 0 to 25, because those are the numbers that are mapped to our alphabet. So the vector 180, 0 mod 26 is 24, 0, and the vector 341, 7 mod 26 is 3, 7. Now our vectors are within the range 0 to 25. Step 10 is to translate these column vectors back into letters. Again, using our alphabetical zero-based indexing, we know that 24 goes to Y, 0 to A, and the vector 3, 7 ends up looking like DH. Our last step is to translate this series of column vectors into ciphertext, or the text that is rearranged so nobody else can read it. Finally, we see that the ciphertext of math is yod, because starting with the leftmost column vector at the top, that's our first letter. Then we move down until we reach the end of that vector. Then we move over to the right and down until we have completed all of our vectors. So, math equals yod in Hill ciphertext.
So after we've encrypted our code, now we need to begin the decryption process. So if you recall, here's our alphabetic zero-based indexing. We have that written out. And also, if you recall, our key matrix is going to be essential to decrypting the code. So basically, the general formula for first finding the inverse key matrix, which is the important part, is the inverse key matrix is equal to the inverse of the determinant times the adjugate of our key matrix K, which is right here. So first we begin by finding the inverse of the determinant. So the determinant here is 15, which is just 15 times 1 minus 8 times 0. So we have 15. And then we have to take that mod 26, but since it's under 26, we just get a value of 15. So next what this is saying is the determinant times the determinant inverse has to be equal to 1 mod of 26. And we're looking for our determinant inverse to be the number times 15 that we get a value of 1 mod 26. So there are some kind of complicated ways to do this, but we just stick to guess and check as it's oftentimes quicker. And we found our determinant inverse to be equal to 7. So next we need to find the adjugate of our key matrix, and the formula for adjugate is right over here. So you just swap the entries D and A around, and you also make B and C negative. So we followed through with that here, and afterwards you have to take it mod 26, and that changed our values from 1, negative 8, 0, 15 to 1, 18, 0, 15. And that's our final adjugate matrix of K. So now to finally calculate the inverse of our key matrix, we take the inverse of our determinant 7 times our adjugate matrix of K, which is 1, 18, 0, 15, and we multiply them out. So 7 times that matrix gives us 7, 126, 0, and 105. And we take that value mod 26 again to make sure it's in our alphabetic range. And we get 7, 22, 0, and 1. And that's our inverse key matrix. Now that we have our inverse key matrix, much of it is similar to the encryption process, and we'll follow similar principles as we do that. So if you recall, our ciphertext was yod, Y-A-D-H. These are our column vectors. So now we take our inverse key matrix, multiply, follow similar steps, and take each of those mod 26. We got 12, 0, 19, 7. And we translated those back to letters using our alphabetic zero-based indexing and MATH, math. So that means that we've followed through both the encryption and the decryption. And that's all.